I'm Klaus Jensen. I'm the Warren K. Lewis Professor and Department Head in the Department of Chemical Engineering at MIT, and I'm a co-founder of SQZ Biotech. So SQZ Biotech provides systems for companies to be able to explore modern biology and transmit materials, a broad range of materials, into cells. In addition to that, they're also developing techniques that will have impact on future therapies. So SQZ Biotech really is a wordplay on the fact that these devices, and like the one I'm holding in my hand, squeeze cells, and so you could also call it, as I did, SQZ Biotech. Delivery of materials into cell have been a long-standing challenge in biology and in therapeutics. And at the time when we started working on this technology, there were basically mostly chemical and biological ways of transmitting material into cells. You could do it either by viral vectors, and that of course has the chance of foreign DNA contamination. You could do it by chemical methods, by cell-penetrating peptides, or you could do it with nanoparticles that have particular chemical functionalities on them. But all of those are very specific technologies and they're limited to certain applications. And then there was the true and tested mechanical way of doing it, which is to use a pipette and a very skilled operator to put it into cells, which of course is very slow and takes a long time to do. We had started to think about using microfluidic systems, and were curious whether we could design microfluidic systems in which we actually used a narrow channel and a jet to introduce material into the cells. And in the process of this research, Armin, who was at that point doing his PhD research, recognized that we could actually transfect materials into cells without having the jet on. And that led then to the whole investigation of how we could design microfluidic systems with parallel channels in which we could squeeze the cells in such a way that we would get maximum transfer of macromolecular material into the cells. The device is microfabricated in silicon. It has a large number of narrow microfluidic channels in parallel so that we can treat multiple cells. The cells enter into the chip, and then there is a narrow entrance region that then follows them into a narrow channel, and in that channel they get squeezed. And then it widens out on the other side. It takes about, depending on the cell types and the conditions, another minute or two before the cells really close up, and during that period additional transvection occurs into the cell. There's a delicate balance if you want to keep when you do this, because if you use too wide a channel you don't squeeze the cell, and so you don't get anything into the cell. If you use too narrow of a channel, you end up squeezing the cell so hard that you tear the cell apart. And so you have to balance the width of the channel with sort of the average dimension of the cell type that you're working with. So you need different types of channels for different cell types. So one of the things that we wanted to show was that this technique was broadly applicable. So we actually worked with many different cell types. And I think we probably, well, by now we're beyond that, but in the early days we brought up around 15 different cell types that we had tried, just to demonstrate that it was broadly applicable. And in the same vein, we also wanted to show that we could get different types of materials or macromolecules and nanoparticles into the cells. So we've done DNA, mRNA, sRNA, we've done proteins, particular proteins that are used for reprogramming. We've done nanoparticles as in quantum dots, and we've shown that these quantum dots can get in collaboration with Wendy and actually remain luminescent and individual dots. And we've also done carbon nanotubes in connection with Michael Strano's laboratory, and show that we can see those carbon nanotubes individually in the cell. Well, so one of the challenges that you always have with these types of techniques is, are you just bringing things in through the cell's own machinery, which is normally an endocytotic pathway that would just bring material in and then probably end up with actually destroying the material in the endosomes in the cells. So we really wanted to show that we could get into the lysosome, let me start that over. So we really wanted to show that we could get it into the cytosol. And so to get it demonstrate that we actually could get it into the cytosol was really a collaboration with Wendy on his quantum dots, because by taking and making a FRET construct that if it is in the system, if you have just this FRET complex, it will luminescent the red. And this FRET complex was constructed in such a way that when it got into the cytosol, the environment in the cytosol will break down the FRET complex and only give you the luminescence from the quantum dot, which is green. And so we actually were able to show that once we introduced the FRET complex into the cytosol, we got the green luminescence. So we could see that they were in fact introduced only into the cytosol. We were also, you could also look at the images of other fluorescent particles that we transferred into the cells. And normally if you get things that come in through the endosomes, you would expect to see the sort of a punctated image, whereas we saw an image that had very uniform fluorescence. So from the scientific standpoint, what remains on the squeeze issue is really to understand the underlying biology, and it is the kind of work that we're continuing to do at MIT. In terms of the devices themselves, I think we have a very good understanding of how to pick the various dimensions and structures of the devices for particular cell types. And the design that we have with multiple parallel channels is, if you will, passively deals with the issue of clogging. They will obviously ultimately fill up, but it takes a while to do that, and we can ensure that while some of the individual channels might fill up, we always have exactly the same speed in the remaining channels, which is important for the squeezing aspect. So the original research at MIT into the technology and that led to the technology was funded by the National Institutes of Health. And as I mentioned earlier, this was originally sort of the idea of a much more complicated device than the ultimately, I think, very elegant solution that we got out of the research. In addition to that, we were fortunate also to have support internally at MIT through the Koch Institute that allowed us to explore and expand the scope of the cells that we were able to handle with the squeeze technology. So in addition to the NIH funding, we were fortunate to have MIT internal funding from the Koch Institute and the Reagan Institute that really allowed us to broaden the scope of the research, both in terms of the cell types we were able to work with, and in terms of also explore new opportunities in immunology.